Hello everyone. In the previous sessions, we have been discussing our probability, and then we started our discussion on conditional probability. Okay, we start our discussion on this. So what we said in the conditional probability, we said that there is some condition, something happened. Okay, so if something happened, so what is the effect on some other thing? So there are events which are not mutually exclusive, and one event might have some common element with the other event. Let's again take an example for the revision purposes. Let's suppose this is our sample space. Let's say there is an event, call it B. Okay, there is some event, call it B, and there is some event, call it A. Let's suppose. Okay, these are the events. Let's suppose these are the elements in the events or something like this. Okay, so now if I am telling you that there is this event A and B happened. So if B happened, what is the probability of A? Now initially, if you see that these elements had some probability, this element, they had some probability assigned. If these events were equally likely, so here we have 6 elements. So each of the element had 1/6 probability in this event A. In this event A. So in the B event, if you see over here, if all the events again are equally likely, so here we again had 1/6. I think this is 7 elements are there. So we had 1/7 probability. Now what I'm saying is I'm saying B happened. So I'm saying B happened. Okay. So if event B happened, this nullifies the possibility that these events like this will happen now, because now I already told you B happened. Okay, what's the probability that A will happen? Okay, if B happened, we are saying that we'll assign these events, these dots, these 4 dots which are outside B as 0. Okay, now there is some commonality between A and B. Now we'll reshuffle these probabilities. Okay, we'll reshuffle the probability like something. Okay, and then we'll say there is some probability of this. I hope that you got the idea. The idea was that if some event happened, and now we'll make the sub event, we'll make this subset of the sample space as our own as our new sample space. Okay, then we saw the 3 approaches. So we said probability of A given B, this was equal to number of elements in A intersection B divided by number of elements in B. And then we said we can also divide it by number of elements in sample space. So we say this is equal to probability of E intersection or A intersection B divided by probability of B. This is what we discussed so far. And even we said we can reassign the probabilities, and we can also compute the conditional probabilities like that. And we took an example also. Now we see that conditional probabilities, they are like Theorem probabilities. They also follow some properties. Okay, this was just a revision. So now we'll see there are conditional probability. They also share the properties that the ordinary probabilities follow. That is, if we have probability of A given B, this will also follow the axiom that this is greater or equal to 0. You will not see that this will be equal to, let's suppose, 2, 3 or something, or -1. Okay, so I'll write a heading over here. So that is conditional probabilities share properties of ordinary probabilities. That's the first property I said that. Unlike, like, let's suppose we have a summation of these probabilities. If some event is there and we sum them, in the previous session we saw that in one example probability was greater than 0, but probability was greater than 1. That time we had some probability of A plus probability of some B or something. So it turned out to be greater than 1. So this can happen. So why can this happen? Because individual probabilities, they cannot be greater than. Let's suppose we have an event in which for that event we have probability of 0.5. Some event can have probability of 0.6. So now if you sum of these probabilities, it can be greater than 1. But individual probabilities, when you calculate, they cannot be greater than 1. So they should be they should lie between 0 and 1. So in this conditional probabilities, they also do follow the same. The conditional probability also is greater than or equal to 0. And where here also we assume that probability of B is greater than 0, because if you see the conditional probability, that is probability of A given B, that is equal to probability of A intersection B divided by probability of B. So we don't want this denominator to be 0. This should be not equal to 0. And by not equal to, now it's a probability, so it should be greater than 0 and less than, obviously less than equal to 1. Now if we have the whole sample space, probability of whole sample space given that B happened, so what should be this? So what do you say? What should be this equal to? If some event happened and we are saying that probability of sample space given this, so what should be this equal to? Because if you know that probability of whole sample space by definition is equal to 1, so this should be equal to 1. So now if you just expand it out, you'll get probability of whole sample space intersection B divided by probability of B. Okay, and this will be equal to probability of B, because intersection between an event and the whole sample space is this B. Okay, divided by probability of B. So this is equal to 1. So again, you see that they are also following the same axioms of probability. Now I'll tell you probability of B given B. So what is this equal to? So this, if we again expand probability of B intersection B divided by probability of B. So B intersection B is probability of B divided by probability of B. This is equal to 1. Okay. Now one more important thing that I want you guys to understand is, let's suppose we have some sample space. This is our sample space. Sample space is the set of all possible outcomes. Then let's suppose we have an event A over here and we have an event C over here. This is our event A, this is our event C. Then let's suppose we have one more event B, which is somewhere like this. This is our event B. Okay, this is our event B, this red event. Now I can also, here you can clearly see that if you see this A intersection C, this is phi. Okay, A intersection C, this is phi. They are disjoint sets, they are mutually exclusive. Then what about this probability of A union C given B? So what about this? So please pause and ponder over this and tell me the answer. So what Dakir said is that we'll expand it by normal conditional probability. Whatever we have defined the conditional probabilities, we'll expand this like that. So that is probability of, consider this as one event now. So this is A union C, okay? Intersection B. That's what we did. If we had probability of A given B, so what did we do? We were doing it probability of A intersection B divided by probability of B. This is what we're doing. Now here consider this as one event. So this is A union C intersection B and divided by probability of B. Now you have seen that in the distributive law we can distribute this intersection onto this union. So we can write A intersection B, okay, probability of intersection B, then union, there is whole union union of A C intersection B divided by probability of B. Okay, now if you know this, these two events again, they are sort of disjoint events. I said that A and C are disjoint. So what I can do is I can write this, the first part I can write this. If you see this intersection part, so I can write this as probability of A. So I can write this probability of A given B, and because this is divided by B, if you see it over here, so I'll just expand it like this. So I'll write probability of A intersection B divided by probability of B, and because now these events are disjoint, so I can write plus probability of C intersection B divided by B. Okay, and this is equal to probability of A given B plus probability of C given B. Is it clear? So probability of,
Yes, sir.
so the question was probability, we are computing probability of A union C given B happened. Yes, so you saw that this became like this. So if you have some disjoint event, so let's suppose you have disjoint events A union B union C now, okay, then you are given D, given some D, so you are told to compute the probability. You can use this to just extend it in the similar way. We can write probability of A given D plus probability of B given D plus probability of C given D, something like this. You can expand it in the similar fashion. So this is one more property that I wanted you to know. Okay, I hope that this is clear. So this is for finite countable events, and we'll also see how to deal with if we have uncountably infinite events. And we'll first have to have the discussion on what is like uncountably finite and uncountably infinite and countable finite, and we'll see things like that. Okay, I hope that these are the properties which I told you are clear to you. Now what the these conditional probabilities, they also follow the same property. Okay, now we'll see what is this conditional probability used for, and we'll take a real world scenario. Okay, then we'll try to analyze that by using our conditional probability. Now first of all, I'll analyze this. Now we'll see models of conditional probability. Models of conditional probability. This is our new heading. So in this, First, I'll define an event and then we'll try to analyze it. Let's suppose we have an event A. So this event A will define it something like this. Like there is a deadly disease in the first session. If you remember that, I asked you a question: if there is a deadly disease, and what's the probability that if a guy tested positive, what's the probability that guy actually has a disease? We'll some sort of now, in the sense of conditional probability, analyze that thing. Let's suppose event A is that there is the disease is there. Let's suppose the probability of disease. Let's say so the possibility of disease, or presence of disease, we can say. Okay, presence of disease. That right. Presence of disease. So then I'll say event B. Event B is tested positive. The test was positive. Test was positive. These are my two events. So event A is presence of disease, and then event B is test was positive. Now I'll construct a tree because we have seen the sequential things. So let's suppose we'll say probability of A. Probability of A means that a person is diseased. Let's say this is 0.05. Let's have these numbers. Like in overall population of 100 people, so 5 people have the disease. Okay, in 100 people, 5 people have the disease. So that is our prior belief. So we believe this, that if we have a general population of, let's suppose, 100 people, so 0.05 probability is this is the probability that person will be diseased. That is, out of, let's suppose, 100, 5 will be diseased. Okay, probability of A complement will be 1 minus this probability of A complement, that is probability that the person is normal, is 0.095. Okay, so we'll start from here. This is our A, person is diseased, and this is our let's suppose A complement, person does not have the disease. This is A and this is A complement. Now we have n the possibilities. The possibility is that the person has this and it was tested, and this guy was also tested. Both of these were tested. Please focus over here so that you can understand this problem in a good manner. So now with the first layer, if you see that, we saw that probability of having a disease is 0.05 and probability of not having disease is 0.95, not 0.095, 0.95. This is 1 minus 0.05. Now we'll see that what is the probability that disease will get detected. So here again there are two chances. The test will be positive or test can be negative. Okay, if it was disease and test was given as positive, so that is A intersection B. Okay, and then we can have like this, we can have, this is B and B complement. B over here, if you see it, this is test was positive and B complement means test was negative. So here if you see this, A intersection B complement. So again in this it would be A complement intersection B. So that is the person was not diseased, but it was detected disease. So this is A complement intersection B complement. Let's name them. So this is our true positive. So actually person was positive, and our equipment, our machine, it also showed positive. So this is called as true positive. Then we had the person actually has had disease, but it was detected as negative. So this is called as false negative. Okay, the false, it was classified as negative. So here if you see now, person he or she did not have the disease, but here our machine or our equipment showed that it has this disease. So here it is false positive. Okay, now this is true negative. How many of you understood this? How many of you understood the set of the problem?
Yes, sir. Got it.
So you got this. So now I in the first day I told you that let's consider that with 99% probability our test is accurate. So equipment is such that with 0.99% accuracy we are getting the equipment to right. So if we just test a patient and we'll get the accuracy of 0.99. So here if you see, this is 0.01 now, again 0.99, and this is 0.01. This is the setup. So now what we are given is, we are given two events, again reiterating the problem. I'm saying that event A means presence of disease, there is disease. So event B is test was positive. Now I'm saying the first possibility is that a person can be diseased or cannot be diseased. So that's what I wrote A complement or A or A complement. A means he had disease. So what is the probability of having disease? 0.05, which I wrote over here. What is the probability of not having disease? This is 0.95. Then I said that now we are testing the patients. So there can be again two possibilities. Test can be positive or test can be negative. So by seeing that, you can clearly see this. So this case over here is when a person had disease and he was tested positive. That's why it's called as true positive. Okay, and then if you see it over here, now in this second branch, the person has actually had disease, but he was told that he does not have the disease. Okay, the test was actually negative, so this is called as false negative. He was deemed as negative, or you are negative, but in actuality he had the disease. That's why this is called as false negative. And then we had this false positive, that is, a person did not have the disease, but the test said that you have the disease, so this is false positive. And then there is true negative. This means that a person was actually negative and the test also said that he was negative. I think the problem setup is clear. Okay, now let's suppose
Yes.
we want to compute something. The first thing that I wanted to compute is probability that the person will have the disease and it will get detected. It will be detected by the machine. It will be detected by the test. This is the first thing that I want to compute. So how can I compute it mathematically? So I'll compute it by using the conditional probability, because you know conditional probability, P of A given B, this is equal to P of A intersection B divided by P of B, and we can also write P of B given A like this. This is P of A intersection B divided by P of A. You now know this from the conditional probability. Okay, so now I want to compute probability of A intersection B. So this will be equal to probability of A multiplied by probability of B given A. Why? So what I'm doing is I'm just taking this over here. So this, from this expression, I can conclude this. So this is what I'm concluding. So I'm saying if probability of B given A is equal probability of intersection B divided by probability by definition of conditional probability. So I can also write it like this. Now I know the probability of A. Okay, if you see, I know the probability of A. This is my probability of A. So probability of A is 0.05. So I also know this probability of B given A. So now given A has happened, this line has happened. So what is the probability of this? So this is 0.99. So multiplied by 0.99. Okay. So can somebody compute what is the value of this? So I'll leave it. They will write the value. Now we computed what is the probability that a person actually will be diseased and the test will say that he is diseased. So this is that probability. Now we'll compute and the probability. We can compute probability of B also. So what is the probability of B? In words it means probability of B means that where is the test positive, in which case the test positive. If you see, test is positive in this case and in this case. Okay, because we have this B over here. So now we need to compute the probability of B. So what it will be? So it will be in this line. So we'll go in here because B is positive, true positive, and then we'll also get this false positive. So in these two cases, we'll have the test as positive, and that's the probability of B. So now what we'll do is we'll say probability of B is probability of probability A, and then we'll go on to this probability of A multiplied by probability of B given A. Okay, then we'll also have plus probability of A complement. So now we'll go on to this probability of A complement. Okay, and but now we got the B also. So probability of A complement given that probability of B given A complement. So these are the only two pathways in which I can get the test is positive. So I'll also compute this. So this will be equal to 0.05 multiplied by 0.99, and then plus this will be 0.95 multiplied by probability that A complement happened, probability of A complement, and then what is the B? This is 0.99, I think. Is it 0.99? Yes. So this is 0.99. Can somebody also compute this? So this is, I think, 0.1445. Has somebody computed this?
Yes, sir. 0.0495.
0.495. So these are the two probabilities. Now, why did I compute this? Why did I compute this thing? Because now the question, if you remember the first session, the question in hand was, what is the probability that a person is actually diseased given that the test was positive? This is the probability that we had to calculate. This is the conditional probability. Okay, now again showing you the picture. So we had two events. The first, presence of disease, the person is diseased or is not diseased. Presence of disease, it can be yes or no. The test was positive, it can also be yes or no. Now we are saying that we have to find, let's suppose we went to the health center, and then what happened there, a person was tested positive. Okay, the person was tested positive. So then some event happened. So some event happened, person was tested positive. Now we want to see what is the actually probability that he was diseased. This is what we want to compute. So don't you see that this is the problem of conditional probability? It can be written like this. It can be written probability of A intersection B divided by probability of B. Okay, probability A is actually diseased given that his test came out to be positive is equal to probability of A intersection B divided by probability of B. Now we computed both of these things. So we computed this. So this is 0.0495, 0.0495 divided by 0.1445, 0.1445. So if you see this, I think it comes out to be 0.34. Okay, even if test accuracy is 99% accurate, but still our probability says that there is only 0.34, that's 34% chances that he will be diseased or he or she will be diseased. How many of you understood it mathematically? Intuitively, how many of still feel that, yeah, this should not happen? Test accuracy is 99%, and still we are getting 0.34%. This looks something like fishy is happening there. So if you see it over here, if somebody told you a problem that 99% accuracy for test and a person was tested positive, and then our intuition tells us that the guy should be actually tested, he should have had the disease. But we missed the point that there is a prior belief also. So prior belief was, this was our prior belief, that probability that person will have a disease in the initial probability was 0.05. Okay, and then after getting the person tested, if he turned out to be positive, now we'll change the belief. We'll update the belief. We'll not change it. Sorry, we'll update the belief, but we'll not change the whole belief. We'll not say that it became zero or something like that. So let me give you the intuition. Let me give you the intuition about this problem. So what we had total 100, let's suppose 100 patients. So out of these 100, out of this 100, 5 people were actually diseased. So let's suppose we conduct test on everybody. So we'll conduct test on whole of these 100 people. So how many for how many people will the test be wrong? So for how many people will the test be wrong? Tell me about this. Like for how many people will the test be wrong? Out of 100, let's scale it up. So out of 1,000, there are 50 patients, something like this. So if you perform 1,000 tests on 1,000 people, out of them 50 will be are actually diseased. So when you perform the test, because you know that accuracy of the test is 99%, so 1% the people will get the wrong, they'll get wrong positive. So if they were actually negative, so they'll get wrong positive. So 19.99 of 1,000 will get the wrong answer. So if they, like, let's suppose we had 950 people, they'll get this. So I'm just giving you an intuition, like how to see this. Actually, the probability that we are calculating is right. So I'm saying out of the 1,000 people, out of these 950 people, and even let's consider 1,000. So how many tests will be wrong? So 1% of the people will get the wrong test. Okay, out of these 1,000, so we'll have, so 0.01, I'll say 0.0% will get wrong. So 0.01 1 multiplied by 1,000. So these people will be like falsely given. So out of these 10 people, so 10 people will be given the wrong label. Okay, so now let's suppose out of these people, you will they'll be added as, let's suppose, positive or something. So if you see this number and this, both of these will get added now. Okay, both of these will get added, and now if actually the person was taken, so the probability will be divided by whole of these numbers. Okay, you run this simulation, have the 1,000 people, and see for how many people, for how many people the test was wrong, and then you see that the even with the wrong, and it captured something like 10 people were wrongly classified. Okay, 10 people were wrongly classified. Let's suppose out of these 60, 10 people were wrongly classified, if you take it like this. So then if you take something like this, so we had I'm just computing the probabilities. So I'm saying even with this smaller number, still the 10 people out of this will be classified as wrong. So they'll actually not be tested as they won't have COVID, but they'll be tested positive. Okay, but this is a huge number. This is a humongous number. So if you see it from that angle, so if we have a huge population, even if there is only 1% of misclassification, the test accuracy, if you see that the test only fails 1% time, but still this one number is a huge. If you take thousands, and if you take even 10,000, now in 10,000 people, it will misclassify 100 people. Okay, in 100,000 people, it will have 1,000 people misclassified. That's why the number came out to be 0.34. So how many of you are now intuitively also convinced that even if you have very high test accuracy, if your test is really good, but if the prior belief itself was very low, if you said that probability that a person is diseased is very low, is 0.05, okay, then probability that even test is positive, so what's the probability of a person having disease is 0.34, that is 34% chances are there. Why? Because of this prior belief. So the line I would like to write here is, with new evidence we update our belief. Please see the world like this. So let's suppose you have some prior belief, you have some belief about the world. So you got some evidence about the belief. You should not change the whole belief. Rather, you should update the belief. That is what this conditional probability is, and that's why it will land us to the Bayes theorem and stuff like that. I hope that you understood this problem. So you saw that intuitively also. If we have a lot number of people, then even if our test is very accurate, 99% accurate, but even for the 1% the people, still it will make huge number of misclassifications. Because of that, the only number we'll get is very less. So if we now perform the test second time, the probability will drastically increase then. Okay, if we perform two tests, consecutive two tests, and one test came out to be positive, second test also came out to be positive, then I think the probability will shoot towards 95, 96%. Okay, because now we'll again update the belief. So because now our belief was updated as 0.34. If you again computed, if you again took the patient for the test and he again came up to be positive, then you will update this belief. I think it comes out to be 0.96 something. You just calculated yourself. I hope that you got the intuition now. How many of you understood this example?
Yes, sir.
Okay,
Yes, sir.
now we'll go to what is called as multiplication rule. Multiplication rule. So what is this? This actually comes from the conditional probability that we just saw. This comes from that. So we'll see this, what this multiplication rule is. I even used it when we were solving this question. So what is this rule? So if you have probability of A given B, that is probability of A happening given that B has happened. So this is probability of A intersection B divided by probability of B. Okay. Now you can just take this B over, and you can just get it on the left hand side and it will get multiplied. So we'll get probability of A intersection B. This is equal to probability of B multiplied by probability of A given B. Now you can generalize this. So this rule is actually called as multiplication rule. Now if you see over here, if you see the things that we're computing in our example, what we're computing, we're computing probability of this, probability of this, probability of this, so probability of this. Now we can directly write. If you ask me what is the probability of A intersection B complement, I can say that the probability is the probability of let's suppose A happening given the, multiplied by probability of B complement given that A has happened. This I can write, or I can write it like this: probability B of B complement given now B happened, B complement happened. What is the probability of A? So this is equal to this. Both the things are similar. Okay. Now let's suppose we have three events. Okay, this can be generalized to more than two events. This can be generalized to 3, 4, n events. So let's suppose now we have three events. So how to prove this now? So let's suppose we are computing the probability of A intersection B intersection C. This is what we are computing. Can somebody can you first give an attempt to compute this and tell me the answer and tell me the rationale behind your answer? So if you have the probability of three events, probability of A intersection B intersection C. So what I said is that consider these two as one event. Let's suppose they are one event. For the sake of argument, they are one event. So we'll write probability of A intersection B. Okay, this is our one event. Probability of A intersection according to what are the multiplication rule we wrote. So this is the rule that we wrote. Probability of A intersection B is probability of B multiplied by probability of A given B. Now we'll write. Let's suppose this is our event. Let's call it E. So we'll just write it like this: probability of E. Okay, and then what will write? Multiplied by probability of uh, C given E. Now we know that E can be substituted. Like our E was equal to A intersection B. So we can write probability of A intersection B multiplied by probability of C given A intersection B. Okay. Now you also can expand this. So this is equal to probability of A multiplied by probability of B given A multiplied by probability of C given A and B. Okay, and you can now expand it to n events also. If you have, let's suppose, probability of E1 intersection E2 intersection En, something like this. So what you can write is, you can write probability of E1 given, now multiplied by, now E1 has happened, probability of E2. Okay, then multiplied by probability of E3. Now given is that E1 and E2 happened, plus, and so on. Like not even plus, this is multiply probability of last event En, given that E2, E1, E2 and everything till En minus 1 happened. Okay, this over here is called as multiplication rule. Okay, so how many of you understood the multiplication rule? This is not just we're juggling with the maths, but you even don't need to memorize it. If you know the conditional probability, you can just get through the, and this is some sort of intuitive also. Probability E happened. First, what's the probability of E happening of E? This is then multiplied by probability E1 has happened now. What's the probability E2? Now these two event happened. E2 and E1 happened. So what's the probability of E3? Something like you keep on doing this. So this is called as the multiplication rule, and this was we got this rule from conditional probabilities. Okay, I hope this is clear. Now,
Yes, sir.
now we'll go to the next topic called as total probability theorem, which will lead us to the Bayes theorem. All these concepts will lead us to the Bayes theorem. Before that, I'll first give you a question so that you also do the question, and you will have at least some reason to revise. Okay, let me give you a question. Let's suppose an urn is there, an urn or a basket which contains 8 red balls. 8 red balls are in the urn, and 4 white balls are there. Please focus on the question, and then you have to answer it. So we have an urn in which there are 8 red balls and 4 white balls. We draw 2 balls from the urn without replacement. Without replacement means I'll draw the first ball, then I'll not drop it back in the urn. But what I'll do is I'll keep it separate. So I'm drawing 2 balls. So I'm drawing 2 balls without replacement. Okay, this is what I'm doing is I have 8 red balls, 4 white balls. I'm drawing 2 balls without the replacement. Okay, the first question is, if we assume that each draw in each ball in the urn is equally likely to happen. So this is the assumption we are having. So we are saying that each ball will just shake it well, and will have that every ball has the probability of each ball is equally likely. So they are equally likely events. So what is the probability that both balls are drawn red? This is the A part. Probability both balls are drawn red. Both balls drawn are red. Okay, this is the first question I'm telling. Can you solve this? So if given any problem, the first step is to mathematically model it. So that is how you should proceed. Okay, that's why the maths feels at least difficult to some people, because they do not get in the math world first. They try to solve something intuitively, and then they don't stumble at the answer. So the first thing, let's do the modeling. So we are saying that we have to compute the probability that both balls are red. So let's suppose for the first draw, we'll say R1. R1 is the probability that first ball is red. This Ri is the event that ith ball is red. Ith ball is red. Now I'm trying to come up with some symbols. Okay, R1 is the first event that when we bring the first ball, and when we drop our hand in the urn, and then we got the first ball as red. Let's suppose R2 is again the same, that second ball is red. So now we got into the mathematical world, if you see it. So now the thing is, we have to compute this probability both balls are red. So what did we have to compute mathematically? Probability of what?
R1 intersection R2.
Right. Nice. So now you try to understand it. First, we try to model it mathematically. Then whatever we studied so far, we'll get into the mathematical world, rather than being intuitive, and then we'll decide, okay, intuition, my intuition tells me. It's better to bring it in the math world, and then whatever rules we studied, apply those rules. Okay, this is like a game. In the initial go, what do? You go to the intuition. Okay, I should do this, I should do that. Then when you find some rules, and then you play by the rules. Okay, so that's what I did. So I had to compute probability both balls are drawn red. The thing is, first I said, okay, let me introduce a variable Ri. This Ri means ith ball drawn is red. So R1 means the first ball drawn is red. R2 means the second ball drawn is red. Now I have to compute probability that both balls drawn are red. So that means probability R1 intersection R2. So what is the formula that you have studied? This is again the multiplication rule. Asrar,
Yes, sir, the one you showed earlier.
Yes,
Probability of R1
R1 multiplied by
into probability of
R2 given
probability of
R1.
R2 given that R1 happened.
R1 happens. So what's the probability of R1? Now we'll compute the probability. So as these are equally likely, so out of 8 red balls, so we have to
take out a 1.
take out 1 ball. So now we'll compute this. So how many possibilities are there?
8C1.
Okay. So 8C1, let's say 8C1. So
Choosing
out
one
of
the
how
two.
many balls are we doing it?
Out of 12, 8 plus 4, 12
8C.
balls. 12C.
This is 12C1. 12C1. So this is
Yes,
the
sir.
first probability. Now this event happened. Okay, without replacement is now it's multiplied by So what about this? What is the probability of R2 being red? Now we are only left with 7 red balls. Okay, 7C1. Out of how many balls we have to compute now? 11C1. Okay, I think this comes out to be 2 by 3 multiplied 7 by 11. So this is equal to 14 by 33. Okay. So how many of you understood this? How many of you understood this?
Yes, yes.
Yes, sir.
Okay, so we said that the first difficulty that people, that most folks they face is that they don't get their thinking in the mathematical world. They think that these things are equations and stuff. But I am always telling you, mathematics is like poetry. So if you understand the language of mathematics, it will be easy for you guys to take a real world problem, map it in the mathematical world, then see the rules of mathematics and see the rules and play with the rules. Okay, the language actually this gives you some sort of medium to communicate. So if I have to communicate with you, let's suppose right now I have to speak English, but English, if you see, is it is there are rules, like grammatical rules, or there are exceptions, and it is having a lot more complex pattern and things like that. But if you see mathematics, there are very set of certain rules. Like if you, for example, we read about probability, there's a probability theory. So in that we found some rules. So what are the rules of the game? The rules of the game are, like, for example, if there are disjoint events, only from the only three axioms, if you see. So from the axiom that probability should be equal to 0 and less than equal to 1, that's the first axiom. And the second axiom was that probability the sample space should be 1. And the third axiom was that if we have two disjoint sets, or if we have two mutually exclusive events, then the probability we can have the probability union of them is the probability we can add these probability individually. These are three axioms, because axioms do not have the proof. Okay, they're what you are believing. So this is the thing that you are believing. That's the baseline. And after that, we build it on that theory. We came up with different rules. I'd like to again give you an example of Feynman. So what Feynman said is R.D. Feynman. How many of you know at least this name? So R.D. Feynman was a great physicist, and he was called as magician of physics. He, I think, was the one of the pioneers who invented quantum mechanics. Okay, so what he said about science is, so he said, let's suppose whole of this nature is like a game. It's like a chess game. It's like a chess game. I'm just taking a digression so that you understand what is my point of telling why is mathematical modeling required. So he said, take whole of this world as a chess game. So now see that nature is playing this game. So in the chess, if there are two players, one player is over here, one player is over here. So both of these players are playing the game. Now there is a third player who does not know any rules. So let's suppose here we have this red player who does not know any rules of the game. So he's trying to observe these two players who are playing. So now they are making certain moves. Let's suppose there's a soldier, and soldier is always going one step ahead. And from this side also, soldier is going one step ahead. Now he makes a rule. The soldier takes one step. Okay, he makes this rule, and after that let's suppose he saw knight. He saw that knight, okay, nice, knight is taking this L-shaped movement or something like that. Then he also saw, let's suppose, queen. So he made a rule, queen is not moving, because he did not see any player moving the queen. He's observing the game, let's suppose, for half an hour or so. But suddenly what happens after he made a set of rules? Okay, these are the set of rules he made. Suddenly the player, he played a move which he did not expect, which the observer did not expect. Now he'll change the rule. So he made a rule, queen does not move, let's suppose. Queen does not move, something like that. But after he saw that player made an unexpected move, what he'll do is he'll change his rules. That's how science works. So if you see, what are we here? We're observers. Nature is playing a game with us. There is this water is coming down, we call it rain, and then we try to see, okay, why does rain happen? So we try to understand the how process. Okay, we try to understand this process, and that's why when we formulate these rules, when these rules are continuously being they are right all the times, you see, okay, it is raining because of this, you keep on testifying your theory, then you make it a fact. Okay, that's where this mathematical modeling gets in the picture also. Now if you have to write these rules, you do not write them in plain English. Okay, you can write them in plain English, then it will require hell lot of work to understand these things. Okay, then books will become probably thousands of pages, 2000, 5000 pages. Now what we have devised, we devised a succinct way of writing that thing in the English. Okay, so if I say 3C2, what's the meaning of this in English? So it has a beautiful meaning. Then out of 3 I have to choose 2. Okay, this is a long sentence in English, but I'm writing it in a succinct format, 3C2. Okay, and even what is the meaning of 4 plus 2? This is, if I have some 4 things, I have 2 more things, so if I put them in the bag and something like that. So this I can write in plain English, but mathematics gives me a level of abstraction. Level of abstraction means now I don't need this, and even you cannot see things from the plain English. You can see the patterns if you write these things in the symbols. So now if you write things in the symbol, so a clear pattern is visible, and that pattern, by using that thing, you can manipulate a lot of things. Now what is mathematics? Mathematics, it models. It is like poetry. If you know language of a poet, so then you can express world differently. Okay, that's why sometimes we say poetry means telling a huge or a humongous concept or a very important concept in few lines. That's what mathematics is for the real world. So if you have to explain a real world phenomenon, so that is you. If you use maths, that's like poetry. And even these equations have meanings. I always tell wherever I teach, I tell them that if you say a mathematical equation, do not be scared of that. Try to translate it into English. Try to translate it into your own language that you understand. Okay, what is, so if I'm writing probability R1, R2, so what's the meaning of this? In English, it is a meaning. The meaning is that what is the probability that R1 and R2 will happen simultaneously? Okay, something like that. So you can translate these things in the English. That's why mathematical modeling is required and mathematical thinking is required. So if you have mathematical thinking, you will think in the terms of maths. So you have a real world problem, you'll map it into mathematics, and then you will play by the rules because you know the rules. You have wrote the rules of mathematics in the probability theory. You'll first see a problem, model it into probability. Now you know the probability rules. Okay, you can play by them. Okay, now we'll go on to the next topic, that is the topic of total probability. This is called as total probability theorem. Total probability. Why am I teaching all of this stuff? Because this whole stuff, this multiplication rule, total probability theorem, conditional probability, this will take us to the Bayes theorem. And Bayes theorem, on that we have a separate field called as Bayesian inference, or we have even in the machine learning we have like Bayesian belief networks, naive Bayes, and a lot of algorithms which are based on this. That's the reason I took some more and more time to explain you these things so that you internalize these concepts. So what is this total probability theorem? So let's now see a picture first, and after that we'll compute this, what this total probability theorem is all about. Let's suppose this is our sample space denoted by omega. Now we have a partition. So what is a partition? Partition means if there are some events, union of all these events, let's suppose is a sample space. Let's suppose this is A1, one partition, this is A2, let's call this A2 and A3. This is our A1, this is our A2, this is A3. These are three partitions. If you see, this is our whole sample space, and this one A1, A2 and A3 is our whole sample space. So now if you take A1 union A2 union A3, this will give you the sample space. That's why they are called as partitions. Okay, they are exhaustive events. Exhaustive events means when we take the union of these, so they come up, they make the whole sample space. Now let's suppose we have another event B, which spreads over these events. Then can be things like this. Okay, now we have the partition. So our partition here is partition, if you see, is A1, A2 and A3. These are three partitions. Okay, then what I have, let's call this having I have some belief. Let's suppose I say probability that AI will happen. This is my belief. I have some, this will be given for me. So I'll say that I'll have some as probability assigned to P A1, A1, A2 and A3. I'll say this is given to me, probability of A1. Okay, now I also might have that probability that B will happen given the AI happened. Because if you see in the real world scenario, so what happened, so let's suppose some A1 happened, A2 happened, A3 happened. Now as you see that this B is spread over these events, some portion of the B is in A1, some portion of the B is in A3, some portion of B is in A2. So what I'm saying is, I'm saying this is the partition. This is how I define the problem. This is how I have the problem. I set up the problem like this: A1, A2, A3. These are the partitions. Okay. So if you take union of these, so all of them they make the sample space. Then I'm saying that let's suppose I have some prior belief. I have said that the probability of A1 happening is this much, probability of A2 happening is this much, probability of A3 happening is this much. Okay. So this is, let's suppose I have some prior information about that. Now also I can have probability, like let's suppose I have what is the probability that A1 happened, probability of B A1 happened. We can have that. So here if you make a tree like this, so this will be probability of A1, probability A2 will happen, probability A3 will happen, something like this. Okay. Now over here we'll have this probability of B. So this will be probability of A will happen, intersection probability of B. So in this here probability A1, A2 will happen, intersection B. Probability of A3 will happen, intersection B. Okay, so this is my thing. So now what I want to compute is, I want to compute what is the total probability of B. Now I have the information that probability of A1, A2 is this much. I also have the information if A1 happened, so what is the probability that B will happen. So probability of B given that A1 happened. Let's suppose I have this information I have. Now what I want to compute is, I wanted to compute probability of B. This is called as total probability. You saw why it's called total. Because the information is, I have this partial information. I have probability of B happening this much given that A3 happened. I also have probability this. I have probability of A1 happening given that probability of B given that A1 happened. So also I have this information, partial information. Probability that A2 will probability of B when A2 happened. This information I do have. So now from that I want to compute the whole probability from this. This is what I want to compute. That is why it's called as total probability. Now if you see that, so you can have the probability of this plus probability of this plus probability of this. Okay, so my total probability will be probability of A1 intersection B plus probability of A2 intersection B plus probability of A3 intersection B. Okay, now I can expand this. I know multiplicative theorem, so I know multiplicative rule rather. So this is probability of A1 multiplied by probability of B given A1. Now both of these twos I know. This also I have given, this also I have given, plus probability of A2 given probability of A2 multiplied by probability of B given A2 plus probability of A3 multiplied by probability of A3 given B. So how many of you understood this so far? Now the setup is like this. Sometimes you will have some events A1, A2, A3 till AN, let's suppose. You'll have n events. So these events will be partitions. What is the meaning of partition? So they are exhaustive events. So all of these events, when we combine them together, they make the whole sample space. Then there will be some event B, which will spread across the whole events, which will spread across A1, A2, or A3, or multiple events. It will spread across multiple events. Okay, we'll take the examples also. So then I'm saying, what if I know probability of AI? If I know the probability of these partitions, if I also know that if a partition happened, what is the probability of B? So I know the partial probabilities about B. So my task is that what is the probability of whole B? That's why it's called total probability. So what I can do is I can write it like this: probability of A1 intersection B plus probability of A2 intersection B plus probability of A3 intersection B. Then I can expand this by using the multiplication rule. So this is what it gives me. So if I write it in a succinct way, so I can write it for n events. If I have n exhaustive events, so I'll write it summation of I goes from 1 to n, probability of AI multiplied by probability of AI happened, probability of B. So this is my probability of B. So this over here, if you see this piece of math, is called as total probability theorem. So how many of you understood this? How many of you understood this?
Yes, sir.
This is what we computed actually. So I hope this is what I computed. I think in first problem also. So if I have to compute what is this probability of B can be, so what is the probability that our event in there? If you just go out away where we had this first problem defined, so we'll see it there and we'll understand the probability from that example. So event B was here. So if you see this event B, so this was test was positive. I'll say overall what is the probability that test will be positive. So I'll compute this. Okay, probability of B. I'll also compute this. I then added them together. Okay, that's what I did here. So I had to compute this probability. Probability of test is positive. So I did probability of A multiplied by probability of B plus A. Probability of AC multiplied by probability of B given AC. So you saw that this event probability of B, so the event test was positive, was spread across multiple events. Okay, this was spread across A1, so we had our sample space something like this. So whole sample space was divided into A and A complement. That is, either it has COVID or it does not have COVID, something like this. A and this was A complement. Then we had test will be positive. Test is positive. It was spread across these. Okay, and now we also knew that. We also knew what did we knew? We knew that if this happened, so what will be the probability of this? What will be the probability of B if A happened? What will be the probability of B if A complement happened? Okay, we knew this. We knew about this. We also knew how we had this belief, prior belief, and then we computed the total this is our total probability. Did you see the example? So how many of you understood? This is very important. How many of you understood this?
Yes, sir.
Asrar, are you there?
Yes, sir,
Zian?
got it.
Yes, sir.
Okay. So I think everybody understood this. So this is what we read so far. So we saw what a conditional probability is. Then we solved a problem. We saw, okay, how to apply this conditional probability. In that example, if you see, we almost applied each and every concept. If you see in there, we applied whole the concept. Now it will take hardly 2 minutes for me to explain you the Bayes theorem. Okay, now we'll go to the Bayes theorem. So the first thing that we covered was conditional probability. Just to give you again the bird's eye view, the conditional probability. Okay, Then the second thing we said, we covered the multiplication rule. Okay, we're just setting up our things for these. The conditional probability we defined for the things first. Then we came up from the conditional probability, we came up with the multiplication rule. Then we saw the law of total probability. We call it total probability theorem. Ability theorem. Okay, again, what we saw this in example. So a patient was there, he can have let's suppose COVID example we took. He can have disease or he cannot have disease. He can have disease, he cannot have a disease, A complement. So in that, test can be positive, test can be negative. So this was B and this was B complement. This was again B and B complement. So here if you see this, so this we named as A intersection B. So this was called as true positive. So this over here was A intersection B complement. This was as false positive, because he was false negative, because he was deemed as negative but he actually was positive. This word here is A complement intersection B. So this was false, I think negative, yes. False positive. This was false negative, I'll say, because here result is actually the person had COVID, so he was deemed as positive, so this is false positive. So this is true negative. So this is as A complement intersection B complement. This is what we saw so far. From this example, we understand all these concepts. Okay. So total probability was, if we have to compute the probability of total B. So B was here and here. We added these two probabilities together then. Okay. So this is what we read so far in the only one slide. Everything that we studied so far is there. Just have a look at there. Pause for, let's suppose, 10 seconds and have a look. Okay. Now we'll go to Bayes theorem. An interesting story about this. Actually, the guy Bay, he wrote this before even like he died. So what happened? He wrote it, and no, he was not having that caliber. He was not having that audacity to publish it. He said that this seems a little bit off. I don't feel this is right. Okay. Then after that, when somebody was looking through his papers and stuff, and he found this theorem, and then after his death, it was published. Okay. So I think Bayes lived. I think he lived from 1701 to, maybe it is written somewhere, 1761. So he lived in this period, and after this it was published. Okay, based on whole of this Bayes theorem, there are whole probability books. You will see there is like Bayesian belief networks, which I talked about. There is whole the machine learning, whole the deep learning, which is based on this Bayes theorem. Okay, and this is called as Bayes rule and Bayes inference. There is one thing called as Bayesian inference. That is whole topic in the whole books have been written on that. That's how important this Bayes theorem is. Okay, now we'll see we'll go into the heart of the Bayes theorem. So what is the single statement? I wrote that single statement even. So what I said is, I said that in Bayes theorem, so what do we do is, we basically, on getting new evidence, we update our belief. This is what we do. This is the whole crux of Bayes theorem, if you ask me in English. Okay, so now how will it be for what will be computing? We'll be computing probability of some AI event AI given probability of B. This is what we will compute through the probability, because if you see it over here, so in the multiplication theorem, I said that we have this probability of A3 given B. So I think I wrote it in the wrong over here. So this is probability of A. Yes, I think it's right. Is it right? Probability of A I given B is like this. So when I'm writing in the summation format. So if you see this, in the example itself, I said these things are given to us. Like probability of A is given to us, probability of B given A1 happened. So what do we want to compute is, so let's suppose we want to compute this, we want to update our belief. We said that, let's suppose B happened. If B happened, what is the probability of AI? This is what we want to compute. Probability of AI given B. Okay, so we had some belief about it, we want to revise our belief. Okay, we want to update our belief. So if you see it in the conditional probability, what can we write? We can write probability of AI intersection B divided by probability of B. Okay, can I write like this? Yeah, this is from the conditional probability. Conditional probability. Okay, now you know that I can expand this from total probability. How can I write it? I can write it probability of AI intersection B divided by summation of I goes from 1 to n, probability of A, let's suppose J, this is J, let's suppose this is J, Aj multiply probability of B given Aj. I think we have something wrong over here. Here, let's write this. This is the total probability. I think we messed up the notations, so I'll write it somewhere. So this is probability of A1. So this is probability of A1. Now, given that A1 happened, probability of B we have to find. Okay, plus probability of A2. Now A2 happened. We have to find probability of B. So that this I wrote in the summation format as probability of AI. Now probability of AI happened given that B. I don't know if I have written it incorrectly or so, but I found I was pretty uncomfortable with the notations. Now this is probability of B. It could have been the same, but I was a little bit uncomfortable. Probability of AI. Now it's right, I think. So we use the same thing over here. So this is by total probability now. So this over here is by total probability. Total probability. Okay. So this is probability of AI given B. This over here is Bayes theorem. Okay, this is Bayes theorem. Or Bayes rule, we'll call it. Okay, even if you ask me, we also computed this. So where? So here, if the test was probability of test was positive and the patient actually was diseased, this is we found this. What is the probability that person will have disease given that the test was positive? We computed it by using Bayes theorem. So going back again. So we first computed A intersection B there. Then we compute total probability. So this over here we use it. If you ask me what we use, we used here multiplicative rule. Multiplication rule. So here by computing probability of B, we computed it by using the total probability. So after that, we use the conditional probability P of A given B. So we said P of A intersection B divided by P of B. Now if you expand this, so this over here, this can be expanded like this. So this over here can be like written as we computed it. So probability of A intersection B was as it is, but probability of B we computed from total probability. Summation of probability of A J is from 1 to n, and probability of B given AJ. So all of this was done in the first example itself. When I took the example on the conditional probability, I did all of these things. I did the Bayes theorem, but I did not tell you that I was doing Bayes theorem. So how many of you felt that now Bayes theorem is not that difficult? So the only statement that you have here is this: on getting new evidence, you do not change your belief, rather you update your belief. Okay, whole of this thing was this. So this is our Bayes theorem. With the first example, please watch this video again and see the flow I went through, because I did not tell you that I am actually doing the question with the Bayes theorem. But at the end, I showed you how I did the whole question with the Bayes theorem. In the first, what I did is I took an example. I used all the things that I had to teach you. I used multiplicative rule without telling you. I used total probability without telling you I'm using total probability. Then even I used Bayes theorem without telling you this is Bayes theorem. That is what I want you guys to learn is if you were present at that time, you should have invented this yourself. Now somebody took this, he made the multiplication rule. Somebody observed this, he said this is total probability. And then when somebody used whole of this, and this was Bayes, and Bayes said that this is our Bayes theorem. And the most important statement I said is that on getting new evidence, you should not change your belief, you should rather update your belief. Okay, with this I'll stop the recording, I'll take the questions from you.